Welcome back, dear students. We continue on our path of understanding the DACs and the ADCs. So now we have already discussed the basic circuit for DAC based on weighted resistors. So as we can see that we have discussed the case of only 4 bits. In this case, handling 4 bits is not a problem, but 4-bit DACs do not find any practical use. For this, we need around 128 bits or maybe 256-bit DACs for giving very high quality, like in the example of music systems. So, what are the disadvantages as we understand? For a weighted resistor circuit to be monotonic, the tolerance of resistances must be less than the percentage resolution. So, even for 4 bits, we have found that the resolution was 1 by 15, that is only about 6.67%. So, that is the resistances should be less than, resistance variation in the resistances should be less than plus minus 6.7%. Just imagine what will happen if the resolution is 1 by 225, that is about 0.4%. Now, for a resistance having a tolerance of better than 0.4%, for a monotonic output, the cost of this DAC would be prohibitive. If it is prohibitive, then it has absolutely no commercial value and it might be used only for defense purposes. Also, 4 bits are not a problem, but the moment we increase it to 8 bits or maybe higher, 16, 64, 128 bits, it becomes unmanageable. Secondly, as the number of bits increase, the range of the resistances becomes a problem. So, for example, for 8 bit, we need resistances like R, 2R, 4R, 8R, 16R, 32R, 64R and 128R, 2 to the power 8, 128R. So, the largest resistance is 128 times the smallest. And for again a 12-bit converter, DA converter, the largest resistance needs to be 2048 times the smallest. Now, this also actually exhibits a practical problem. The resistance values cannot be so far apart because the current passing through the circuit becomes unmanageable. At one point, you would have a milliampere current and divided it by more than 1000 times, it comes down to below microamps. And because of this tolerance and range problems, the mass production of weighted resistances, weighted DA converters becomes impractical. So, the solution is having R2R ladder method. In this R2R ladder method, we have resistances which have only 2 kinds of values. One is R and one is 2R. And since these resistances are on the same chip, they have almost identical characteristics and hence this minimizes the tolerance problem. So, if we look at it in another way, as the number of bits increase, the integrated ladder can divide the current much more accurately than in the case in binary weighted resistances. So, if we look at this circuit, we will find that we end in a 2R, and as we go back we have a R, then again a 2R, again R, and this forms a kind of ladder. So, these 2 resistances are sometimes taken to be in parallel, and as we will see how this is minimized, and we will see that for all practical purposes this DAC with R2R ladder method offers practical solution to our problems of D to A conversion. One of the famous IC numbers is DAC 808, that helps, and many students perform experiments in class. So, what really happens is that when we have this ladder network, we will see that the final R and the branch in the branch will see this R and this R. While looking into the circuit, just like our Thevenin's theorem, if we look into the circuit, we will see that these two R's that are shown in the top figure on the right are in series, and together they add up to form 2R resistance. So, if we look at the node C, then we will see that this 2R is in parallel to the existing resistance 2R. So, effectively parallel combination of two 2R resistances gives us a value equal to R. Again, from point C, we will see that this node between B and C, we have a resistance R. So, the equivalent resistance that we obtained for the node C was R. Now, that R and B and C R again are in series, they add up to 2R. So, that is in parallel with the 2R resistance already fixed as a branch in node B. So, again we will have parallel combination of two 2R resistances, and these two will again give you the value of R. In this way, finally what we are left with is a resistance that has a value of R. Now, the main problem with binary weighted resistance was the value of resistances became unmanageable, especially when we increased the number of bits. Now, that is not a problem that we would face here. First, the current became unmanageable in binary weighted, because for a typical 128-bit DAC, the current, as we found, varied from milliamperes and down to microamperes. But here, since the resistances are only R and 2R, therefore, that resistance influencing current values is not there. We can, according to our requirement, we can fix the value of R and hence 2R. For example, we need to understand whether we need a DAC for a disc jockey, a DJ, for DJ performance. Now, for a DJ performance, I would require a DAC that handles high current, because we play music on large speakers and the driving current over there is quite high. So, therefore, the R value would be quite low in the case of a DAC that we would like to use in the case of a DJ. However, for portable equipment that we use in the fields, we require minimal current. That's because we just want to acquire data that we actually save on our portable hard disks. So, in this case, what really happens is we can put the resistance value a bit higher, so that only minimal amount of current flows in the circuit, and that minimal current that flows in the circuit would effectively reduce the amount of current consumption of the circuit, and hence the circuit can behave or operate for a longer duration on battery. So, depending on the type of application and on the place of application, we can have same DACs being configured in different manner. So, this is where R2R ladder network scores, where you can actually tailor the magnitude of resistance that one is using. So, moving forward, we see that this is the circuit for a DA converter with R2R ladder network. As we can see that in this case, we are using a constant current source, which you can see on the left of the screen. That constant current source supplies the current that is collected by the circuit via again 4 switches in this case. So, in the previous case of DA converter with binary weighted resistance, we used a voltage reference which was high precision. In this case of DA converter with R to R ladder network, we use a constant current source. So, now looking at the circuit, we see that again there are 4 switches, and the switch on the left of your screen would be the MSB, and the switch on the right of your screen would be the LSB. That is because the MSB will have the maximum current and LSB will have the minimum current. So, looking at the right hand section of the screen, we see that we have a 2R resistance end for the ladder. This 2R resistance is in parallel with the branching 2R resistance at node D. Now, 2R and 2R parallel would give you R. So, hence again D branching resistance going downward became R due to parallel combination of 2R resistances. Hence, this R is again in series with the branching resistance from the flat resistance, horizontal resistance C. Now, R and 2R in series again gave us 2R. So, this resistance of 2R is seen to be in parallel from the node C and is parallel with 2R resistance that is branching out from C. So, so on and so forth, we can see that in this case we use minimal variation of components, that is resistance. Here also the tolerance will not matter that much like in the previous case, and since we are not using a whole range of resistances, hence making this circuit, tailoring this circuit for personal use becomes much easier. Hence, for all practical purposes, R2R ladder network of a DA converter is preferred over binary weighted resistances DA converter. So, when we move on to the switch positions, we see the total current as having D3 since there are 4 bits. So, we go from D0, D0 to D1 to D2 to D3. So, D3 has the maximum value, D2 is 2 to the power minus 1, that is 1 by 2, D1 is 1 by 4 and D0 is 1 by 8. So, again in this case that there is a value of steer current, and what is steer current? By current steering we mean that the current throughout the ladder remains constant and all that changes are at the ground points. This is to ensure that we do not have superposition problems and we do not, and hence no stability problems. So, the constant current implies that constant voltage occurs, and which means that stray capacitance in the ladder has very little effect. So, this is where we end the comparison between R2R ladder network and binary weighted resistor of DA converter. Now, we move on to the complement, that is AD converter. As you can see from the figure that we have AD converter. This AD converter has analog component. At the top left we have an operational amplifier which is configured in open loop configuration. So, that the moment we see an op amp in open loop configuration, we understand that it is designed to work in saturation region. So, the output would be either be plus saturation or minus saturation. in the circuit, you can also see that there is a counter. You can see the counter, and then it ends. It goes in a U shape from left to right. You see the output of the op amp going into the counter, and then from the counter we see it is being fed into 8-bit DA converter. So, and the output of the DA converter is again fed to the op amp. Now, looking carefully, what are the three most critical things that we see over here? First is op amp configured in open loop configuration, one 8-bit DA converter and one counter. So, what is a counter? We had seen before that counter is digital circuit that counts up or counts down, that can be configured to reset itself, and that is can again be tailored to count either up or down. So, depending on the number of bits that we are handling, we will see that we need to use a counter that is compatible with that. So, in this case what we find that the outputs are D7, D6, D5 dot 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 D0. So, therefore, this is an 8-bit AD converter. So, as you can see, where is the analog signal being fed? The analog signal is being fed to the op amp, and we have fixed the other input of the op amp as our reference. So, if we look at the op amp in exclusivity, then we see that it will change state only when the reference voltage is exceeded by the input, or reference voltage remains same and the input becomes less than the reference voltage. Any change in the difference between the two signals would change the output of the op amp from positive saturation to negative saturation. So, looking carefully, as we can see that the plus is at the top, the non-inverting input of the op amp is at the top and the inverting is at the bottom. So, therefore, if the input signal, that is the analog signal, is more than the reference signal, then the output of the op amp would forever be in the plus saturation. The moment the input voltage, input analog voltage of the op amp falls below the reference voltage, we will see that it goes, the op amp would change state to minus saturation, negative saturation. So, basically the op amp in open loop configuration is being used as a comparator. It is comparing both its inputs and seeing that what is happening and whether it needs to change from plus saturation to negative saturation or vice versa. So, this is being used, this comparator is used as a control signal in this circuit. Hence, let us look how it works. First, you feed the input signal to the positive terminal of the op amp and the reference to its negative end. So, it goes to positive saturation. At positive saturation, the counter keeps counting. Initially, the counter is reset to 0, 0, 0, 0, 8 times zeros, that is D7, D6, D5, D4, D3, D2, D1, D0, all are kept zeros. So, the output is taken as 0, 0, 0, 0, 0, 0. This is again fed to 8-bit DA converter. This is digital, it converts into an analog voltage. That analog voltage with one increment is fed into the negative terminal of the op amp, configured as a comparator. Now, the comparator compares the difference in the inputs of the input signal that needs to be converted from analog to digital and the signal being fed from the 8-bit counter, 8-bit DAC to the comparator. as long as the input signal is more than the output of the 8-bit DAC in the op-amp comparator, the output of the comparator, that is op-amp, would be there in positive saturation. And the counter that we have here on the right of the screen would keep incrementing itself. So, suppose I had for 8 bits, I had around 5 volts being fed. So, every time if there is an increment of 1 volt, then what happens? First, our input voltage was 5 volt, that is fed to the comparator at the positive terminal, and the negative terminal was initially at 0. So, the op-amp comparator gave a plus saturation. So, plus saturation being fed to the, in this case, the counter. So, that counter counts up from 0 to 1. That 1 is in digital form and is fed to 8-bit DAC. That 8-bit DAC gave an output of 1 volt. Now, this 1 volt was again fed to the comparator. So, 5 minus 1 was still a positive. So, therefore, and 5 was greater than 1 was positive. So, therefore, the op-amp still remained at positive saturation. So, again the signal was fed to the counter, that counter counted up, it became 2. When it became 2, it is again in digital. So, therefore, the 8-bit DA converter converted this 2 into analog. That analog voltage was again fed in the op-amp. Now, 5 minus 2 was still positive. So, therefore, 2 more cycles were conducted and we found from 2 to 3, 3 to 4, and then it became 5. The moment the output of the 8-bit DAC became 5 volts and was fed into the op-amp, then effectively the input voltage that was initially taken to be 5 volt, we have 5 minus 5 not exact at both the points, and hence the output of the op-amp now changed from positive saturation to negative saturation. And therefore, this change from positive saturation to negative saturation actually stops the counter from counting any further, and we have the output from the counter in terms of digital output of D7, D6, D5, D4, D3, D2, D1, D0 as equal to 5 volts in decimal. So, in this way we are able to convert the analog input into digital output. There are a few things that we need to take care of while we are feeding in analog voltage to the op-amp. The op-amp must be configured in open loop configuration. In open loop configuration, the gain is very high, of the order of 200,000, that is 2 lakh. So, the op-amp would behave or operate only at positive saturation and negative saturation. If the input analog voltage is very small in the order of microvolts, then this circuit will not give a very stable response. The stability of the circuit depends upon the input that we are handling. For low current analog inputs, we have specific operational amplifiers, and the one that we have discussed in our earlier lectures, that is the 741, would not suffice the requirements of this circuit. So, as we understand that AD converter is much simpler provided we understand we use card technology. If we are going to design the AD converter using discrete components, then it becomes quite complicated and troubleshooting this circuit becomes very, very strenuous. So, in this case, we see that AD converter uses analog components and digital components simultaneously. The 8-bit DAC in itself is a hybrid of analog and digital components. The counter, on the other hand, is purely digital, and in this case the comparator that is configured using other op amps or this op amp is entirely analog in nature. So, with this, associated circuits and DA and AD converter, we are able to, humans have been able to process digital signals which are much easier to process compared to analog signals. Digital, why digital scores over analog? We need to understand, and that is that digital is cheap, digital is fast, and hence, since we have only 2 bits to take care of, high voltage, no, 0 voltage, high current, no current, only 2 states to take care of. So, hence processing digital signals does not require extensive electronic components, rather it requires only specific and precise components. So, hence digital circuits are preferred over analog. At the same time, we should understand that the performance, if price is not a factor, then the performance of compatible analog and digital components are compared, then analog is always better than digital, since it takes care of continuous variation. Digital scores, because we are able to reduce the price, and hence it becomes cheap. And besides that, digital components help us gain speed. What we understand in computers nowadays, the minimum speed of the clock is around 2 gigahertz, and for gaming laptops it goes around 4 gigahertz. Hence, we come to a close as far as your analog and digital technology is concerned, and we have today discussed DAC and AD converter. So, happy learning and thank you.